This is Liziba Station in Chongqing. To manage the city's extreme lack of space, engineers designed the transit tracks to run directly through the 6th and 7th floors of this residential high-rise. This integration answers a demographic reality. 1/5 of the world's population is squeezed into these eastern regions, creating extreme urban density. Overlaying topography reveals the trap. Towering mountains, river systems, and shifting deserts box them in against the coast, making horizontal expansion nearly impossible. Conventional infrastructure projects often fail when faced with these heights and distances. A standard bridge or highway simply cannot withstand the shifting forces found in these extreme environments. Connecting these regions required a complete departure from traditional building standards, leading to the development of specialized materials and automated logistics designed specifically for high-stress geography. These megastructures are functional solutions to a state of geographic warfare. They are designed to reclaim livable space from an environment that would otherwise reject it. In the Western Mountains, sheer elevation acts as a physical wall, keeping remote communities isolated from the medical and economic resources of the lowlands. In villages like Atulir, the daily commute meant navigating rotting vine ladders up a sheer cliff. Replacing those vine ladders with these modern, anchored steel stairways reduced a dangerous 3-hour climb down to just 40 minutes. On a larger scale, the Duji Bridge spans the Bipan River Canyon at a height of over 560 meters. It slashed travel times across the region from 5 hours to just over 1 by simply stepping over the mountain range. Higher up, the Qinghai-Tibet Railway reaches altitudes of 5,000 meters. At this height, the thin atmosphere makes even basic physical activity dangerous for most travelers. To solve the biological challenge of the thin air, the train cars are fully pressurized. This system maintains a constant flow of supplemental oxygen, allowing passengers to cross the roof of the world without succumbing to altitude sickness. Conquering verticality is a matter of environmental management. These projects prove that with technical intervention, even the most oxygen-starved heights become accessible to the public. Beyond the mountains, engineers must also stabilize terrain that is in a constant state of motion, such as shifting sand and massive river volumes. In the Taklamakan Desert, the sand dunes are perpetually moving. To keep the highway from being buried, planners installed thousands of these straw grid structures and planted drought-resistant shrubs to anchor the soil in place. Dealing with the Yangtze River required mass on a different scale. The Three Gorges Dam is the world's largest hydroelectric station, acting as a massive concrete anchor for the nation's energy grid. To keep cargo moving past this 180-meter wall, engineers built a hydraulic ship lift. It functions as a marine elevator, hoisting 3,000-ton vessels over the dam in about 40 minutes, a fraction of the time required by traditional locks. However, dams naturally trap silt, which can clog the reservoir. The Shaolongdi Dam solves this by releasing water with explosive force to flush the sediment downstream, a process so massive it has become a global media spectacle. Mastering the flow of nature requires kinetic engineering. These systems don't just block natural forces, they use mechanical energy to dynamically manage and vent them. In the urban core, the geography becomes entirely artificial. Engineering must now solve for extreme density and a total absence of horizontal space. As buildings reach super tall status, they face the physical pressure of typhoons. The Shanghai Tower uses a specific 120-degree spiral twist to reduce wind loads by 24%, ensuring stability during extreme storms. Extreme density pushed commerce underground. In Chengdu, shopping centers are built entirely beneath public parks, utilizing subterranean space to keep the surface green and breathable. Managing this layered density requires a digital brain. The Chengdu Supercomputing Center processes a quadrillion calculations per second to manage the complex logistics of energy, traffic, and emergency response in these hyper-dense zones. This processing power manifests in the sky. Hundreds of synchronized drones replace traditional fireworks, using high-precision algorithms to tell complex stories through autonomous light shows. In these cities, the distinction between physical architecture and digital intelligence has disappeared. The buildings and managing software have become a single, integrated environment. Historically, humans built static barriers to survive the elements. fixed stone structures like the Great Wall that worked by simply standing their ground. Today, that survival strategy has evolved into something dynamic. Modern infrastructure now uses data, robotics, and adaptive materials to harmonize with the environment, rather than just resisting it. These solutions are becoming relevant globally. As metropolitan areas worldwide face rising sea levels and shrinking habitable land, the technical data gathered from these projects provides a practical guide for urban expansion. The techniques used to stabilize shifting dunes and pressurize high-altitude transit are empirical proofs that human activity can be maintained in environments once thought to be uninhabitable. We are seeing the results of stress testing the limits of the habitable world, moving toward an era where every city must operate with this level of technical integration. By solving for the planet's harshest geographic constraints, these projects demonstrate the technical reality of how our cities will likely have to function in the coming decades.